This beam is rotating because the load is applied away from its balance point. In structural analysis, we simplify distributed forces, like the weight of the beam itself, by assuming they act through a single point. When that point is placed exactly at the centroid, the forces align, neutralizing the twisting moments that would otherwise cause the structure to tilt or fail. For a perfectly uniform material, three distinct physical concepts overlap at this center. The center of gravity is where the total weight acts, the center of mass is where the total mass is concentrated, and the centroid is the purely geometric center of the shape. But if the density is uneven, the geometry and the mass separate. If we replace half of this block with dense lead, the center of gravity and center of mass shift toward the denser material. However, because the outer dimensions haven't changed, the centroid remains locked in the geometric center. Because most engineering problems assume a uniform, constant density, these 3 points are treated as one. This allows us to solve complex physical weight distributions using nothing but the properties of the shape itself. We can simplify our calculations by using established formulas for fundamental shapes. For any triangle, the centroid is located exactly 1/3 of the height up from its base. For a semicircle, it is found at a distance of 4r over 3 pi from the flat diametrical axis. Symmetry provides an even faster shortcut. If a shape is identical on both sides of an axis, its geometric center must fall on that line. For this T-section, the vertical axis of symmetry immediately defines the x-coordinate, removing the need for any complex math. Checking for symmetry is the first step in any statics problem. It defines the centroidal axis and determines where the internal stresses will be zero during bending. To find the balance point of a complex system, we use a weighted average. Consider these two particles, a 2 kilogram mass at coordinates 2, 4, and a 3 kilogram mass at -3, 5. By multiplying each mass by its coordinate and dividing by the total mass, we find the system's equilibrium. For these 2 points, the center of mass sits at -1, 4.6. We apply this same logic to two-dimensional surfaces by breaking complex sections into simple blocks. An asymmetric L section can be sliced into 2 distinct rectangles, labeled Area 1 and Area 2. Accuracy depends on a single fixed reference. Before calculating, we must establish a global x and y axis, usually along the bottom and leftmost edges of the entire shape. We then locate the centroids of each individual rectangle. Crucially, these coordinates must be measured relative to our global origin, not the edges of the individual blocks. We then sum the moments of each area, multiplying each individual area by its distance from the axis, and divide by the total combined area. This gives us the y-bar coordinate for the entire composite shape. This process works because calculating a composite centroid follows the same mathematical averaging as our particle system. We are simply treating each geometric area as a localized point of mass. We can also use this method to account for empty space. If we have a rectangular plate and punch a circular hole out of its center, the balance of the shape changes. Mathematically, we treat this cutout as a shape with a negative area. The large rectangle is a positive value, while the circle we removed is represented as a negative area in our summation. Try setting up a coordinate table for this plate. Assign a positive value to the rectangle and a negative value to the circular hole. Then apply the weighted average formula. Subtracting the hole's area moment from the total shifts the final centroid. The result shows the balance point migrating away from the void and toward the remaining solid material. In engineering mechanics, subtraction is the addition of negative weights. This allows us to find the centroid for any shape with cutouts, voids, or fragmented parts. When an object features continuous curves, we can no longer rely on simple blocks. We must use calculus to find the balance point. Consider a solid hemisphere with a 16 millimeter radius. We analyze this by slicing the hemisphere into an infinite number of thin disks. Each disk represents a differential volume, dV, which is defined by the area of the circle times its thickness, dy. We substitute the geometric relationship, x squared equals r squared minus y squared, into our integral. We then integrate the moment of volume from the base up to the full height of the radius. The integration reveals that the center of gravity for a solid hemisphere is 3/8 of the radius. For our 16 millimeter model, the balance point sits exactly 6 millimeters above the base. From a single wire to a three-dimensional solid, the principles of centroids allow us to predict exactly how a structure will respond to load and gravity. To maintain accuracy in any mechanics problem, follow these three principles. Use lines of symmetry to find coordinates without calculation. Treat holes and voids as negative areas. And always measure every component from the same fixed global reference axis.